In this section, we'll be discussing the independence of two events. And for this situation, we're going to start with what we'll call just an intuitive definition of independence. And for that, we'll say that two events are said to be independent if the probability of B conditioned on A is just equal to the probability of B. And another way to look at this is to say that really the occurrence of A, the fact that A has occurred, doesn't give us any new information about B. Again, the probability of B being equal to the probability of B conditioned on A means that whether or not A occurred, the probability of B is still the same. It's a really intuitive definition, but it's not necessarily that valuable because for this to work, we have to have an event A that has a probability greater than or equal to 0. Remember, that was one of the conditions of, well, conditional probability. But as you may recall, we have a different form of the probability of B conditioned on A. And originally we said that the probability of B conditioned on A would be equal to the probability of B intersected with A divided by the probability of A. And that was just our definition for conditional probability. Well, if we get rid of this conditional in the middle, we can create a new formal definition that does not require that A be equal to 0. And that is just from rearranging the terms. And so the formal definition of independence basically says that the two events A and B are independent if the probability of A intersected with B, or as we have up here, the probability of B intersected with A, remember those are the same, but the probability of A intersected with B is equal to the probability of A multiplied by the probability of B. And we get that just by multiplying both sides of this equation here by the probability of A, which gives us that the probability of B intersected with A then is just equal to the probability of A multiplied by the probability of B. And again, this is the formal definition of independence, which doesn't require that we have a probability of A greater than or equal to 0. Now, again, the advantage here of this formal definition, kind of walking through all of the advantages, the first one is that it's symmetric with respect to A and B. The order of A and B doesn't matter. Remember, this is just multiplying here, and we know that multiplying, you can swap the order of those terms with no impact. And the same thing applies with this intersect. If we go back to our laws of probability, we can say that A intersect B is equal to B intersected with A. So the order of events, whether we choose A first or B first, doesn't matter. Now, the other thing here is based on where we started with our intuitive definition, we actually have reverse implication that the probability of A conditioned on B is equal to the probability of A. Now, remember our original starting point was that the probability of B conditioned on A was equal to the probability of B. But now we have both ways. We have both conditions covered, whether it be conditioned on A or conditioned on B. Both of those are covered through this definition of independence. And then finally, like we mentioned earlier, it does not require that the probability of A be equal to 0. So using this definition, let's go ahead and work a problem. So let's say that we have a bowl, and in that bowl we have 4 red marbles, 3 blue marbles, 2 blue balls, and 5 red balls. So the question we might ask here is the event R, and we'll say that's just the object being pulled, whether that's a marble or a ball, being red, is that event independent of the object being a marble? And we'll call that event the event M. So for these events, the event R and the event M, to be independent, we must show that ultimately this equation of independence holds true. So we would say that for this to be valid, for these events R and M to be independent, the probability of R intersected with M must be equal to the probability of R times the probability of M. Again, this is really the probability of the event being red and of the event that it's a marble. But taking that out, we can calculate all of these probabilities. So the probability of the intersection of R and M is the probability of drawing a red marble. And there are a total of 14 objects in this bowl, and you can get that just by summing up all the different elements here. But with this, we can say that the probability of pulling a red marble is just equal to 4 out of the 14 total options. And in order for this independence to hold up, then that 4 over 14, the probability of getting a red marble, must be equal to the probability of it being red multiplied by the probability of it being a marble. And so the probability of it being red would be 4 red marbles plus 5 red balls, so 9 out of the 14 objects. And then we would multiply that by the probability of a marble, which would again be the 4 red marbles plus the 3 blue marbles, which would be 7 out of the 14 total options. Now, if we calculate this out, we'll find that the right-hand side of this 9 over 14 times 7 over 14 is equal to 9 out of 28. And so what we've proven here is that 4 over 14 is not equal to 9 over 28. And so therefore these events, the event R and the event M, are not independent. Now, let's look at a different example here for a second. If we have a space, a sample space with two events, A and B, and you can see just from the way that these are drawn that A and B are disjoint if we go back to our set terms. So the question we might ask is, well, are A and B independent? Now, disjoint and independent are two different terms that we've derived. Disjoint, you may remember, is that neither of the sets has anything in common, and independence is that the two sets don't have any impact on the other one occurring. So there's a formal proof for this that we can go back and use our equation for independence to prove, but then we'll come back and look at more of a intuitive way to understand this. And so if we utilize our equations, the first thing we need to calculate is the probability of A intersected with B. And the probability of A intersect B, well, since there's no area shared between these, there's no outcomes shared between these events, it doesn't matter how many total events there are. There's 12 in this situation. But we can say that this probability is 0 out of 12. Then we need to compare this to the probability of A multiplied by the probability of B, which we'll find is, in this case, equal to 6 out of 12 and 4 out of 12, respectively. So that would be 1/2 times 1/3. And as you probably guessed already, 1/2 times 1/3 is a positive number, which is not equal to 0. So in this case, we would say that these two events are still not independent. Now, the other way to look at this is we ask the question, are A and B independent? And this is getting back to that informal proof that hopefully will help things click a little bit. When we first said the definition of independence, we said that the probability of B conditioned on A must be equal to just the probability of B. Well, when I first start looking at this, the probability of B is some value greater than or equal to 0. But in this specific situation, it's just greater than 0. But because A and B are disjoint, the intersection of A and B will always be 0 events. So for this situation to hold true, we would have to have an A and a B that both have 0 events in order for them to be independent. But assuming that's never the case, because we're always interested in events that have at least some probability, we can say that by the fact that these two are disjoint events, if I had an outcome in A, I can now guarantee by the fact that these are disjoint events, by the fact that they have no elements in common, that there is a 0 chance of the event B occurring. Again, the same is true the other way. If I have an event or an outcome in B, then there is 0 chance that an event in A could occur. So these are actually the exact opposite of independent. They are what we would call mutually exclusive, but because they have 0 events in common, knowing that A has occurred actually tells us a great deal about B. It tells us that it can't occur. And so disjoint is actually the exact opposite of independence. So with that knowledge, let's go ahead and look at another example just to kind of reinforce this. Let's say that we are looking at a bowl, and this bowl, again, same bowl as we were looking at before, has 4 red marbles, 3 blue, 2 blue balls, and 5 red balls. And the question that we'll ask is the event R, the object being red, independent of the event B, the object being blue. Now, the object can only be either red or blue. So these are disjoint events. And based on our previous example, this should be, again, mutually exclusive or disjoint events. And so therefore, they should not be independent. But let's go ahead and plug these numbers into our equation just to raise our confidence level that this holds true. So if we look first at the probability of red intersected with blue, this is the probability that the object we pull is both red and blue. We can say that very easily that is equal to 0 out of the 14 possible outcomes. And then the other side of this equation would be the probability of red times the probability of blue. Well, the probability of red in this case is going to be 4 of the red marbles plus the 5 red balls, so 9 out of the 14 outcomes. And the probability of blue is going to be the 3 blue marbles plus the 2 blue balls, so 5 out of the 14 outcomes. And when we multiply this out, either way, we can look and say very quickly that these are something greater than 0, that it's not equal to 0 out of 14. So in this case, we've shown that these events are disjoint, right? That was from this part right here. But more importantly, we've shown again that they are not independent. And mutually exclusive events or disjoint events will never be independent.